Hello, my name is Alex Hart.
I'm Donnell Smith.
And I'm Tom O'Donnell.
And we're going to be giving a short presentation on buffers and the common ion effect.
So the first major topic for buffers is the common ion effect. And basically what this means is that for something like acetic acid, as we have here, you would take its conjugate base and you'd make a solution of it. So for example, we would use sodium acetate, Na. Now this is a strong electrolyte, so it'll fully ionize in solution. Now, acetic acid is a weak acid, so it only partially ionizes. So if we have a solution of the sodium acetate first, and then we add in the acetic acid, or even the other way around, it's going to suppress its ionization because it's going to fully ionize. So you're going to have a larger concentration of the acetate ion, which is then going to shift this equilibrium to the left, and it's going to go back to acetic acid.
And the reason we study buffers is because they're very important biologically and in our everyday world. Because the way it works is that only certain enzymes can work in our bodies if they're at a particular pH range, and we can only have certain reactions in our body go to completion if they're at a certain pH range. And that's why our blood is like a very important buffer system in our bodies. And I'm going to show you how we actually calculate the pH of a buffered solution using the Henderson-Hasselbalch equation. What I'm going to do is I'm going to derive the Henderson-Hasselbalch equation for you real quick using the Ka equilibrium expression. So we have the Ka equals the concentration of H plus times the concentration of A minus over the concentration of the acid. And what we can do is we can take the log of each side. So we have the log of Ka equals the log of H plus, or H plus times the concentration of A minus over the concentration of HA. And based on our properties of logs, we can break this up into the log of Ka equals the log of the concentration of H plus the log of the concentration of A minus over the concentration of our acid. And what this becomes is the negative pKa equals the negative pH plus the log of A minus over our acid. And we want to get rid of these minus signs, so we just switch their sides. And we get the pH equals the pKa plus the log of our initial concentration of the conjugate base over the initial concentration of our acid. And this right here, that is our Henderson-Hasselbalch equation, and that's the equation we would use to calculate the pH of a buffered acid solution.
Okay, so now with that, let's look at a problem with a buffered solution. So we're going to use this equation down here. We're going to use the Henderson-Hasselbalch equation. We're going to get our pH. So down here we have the equilibrium equation already set out with the pKa there. So our concentrations of these two for our HA, which is our acetic acid, is going to be 0.1. And we have a 0 here for our H plus. We're going to have 0.4 more for our A minus conjugate base. pKa. So 4, 5. So log this is going to give us a pH of 4.347.
So then, if this solution wasn't buffered, we would have seen that with the regular Ka equilibrium expression, the pH would have came out to about 2.87, which is significantly lower than the buffered solution's pH, which was 4.347. This shows how strong of an effect a buffer can have in trying to resist that pH change.